welcome to the stream. How are you doing? Are we live yet? Everything works. Johnny, you were wrong. My microphone worked from the start. Hello, Ulyss. Hey, Johnny. Hey, Dutch. Hey, Dishipu. Hey, Jordy. So, I'm not feeling well today. I'm frustrated because I know you want a good mood from me. So few things worked today. I'm also working on this PCB for a whole week and with no advances. But I hope we can make some progress today on stream. So this will be purely PCB design today. And yeah, big work is tiring. Okay, you know what? We start with a booster, not sponsored. I just need something. Hey, Mr. Triad. Hey, Sonic. Hey, Christian. Yeah, of course something doesn't work. What is going on? Wait. Does it update? Who knows? No. It does. Okay, yeah, here we go. It's called. I have also old tea in a. Is this a Hackaday cup? Yeah, a Hackaday mug. Cup mug. Start up with Freenet Branca instead. Always makes you feel good. What is that? Freenet Branca. Oh, Fairnet Branca, nicht Freenet. Oh. Quebec, yeah. Quebec. So, tell me something entertaining. Should we do something else first before we start PCB design? Because this will be, I'm, you know what? I will give you some updates. Oh, do you want to see a time lapse how I ripped off, like destroyed, like removed the ceiling? I continued a little bit of renovation and now I got all the materials, not all the materials, most of the materials to continue making. Where's this adapter? Can't see the adapter. Huh? Oh, here's the adapter. If you're interested, but let's not do it. Hey, Jesse, Harry. So, yeah, I don't. It's just a short time lapse of me. You will see the complete renovation update at some point. I will just give you an update on what was going on with that stuff here. I almost said crap. Okay, so I don't know what was the last time we talked about the design, the KiCad design. I probably should have switched to Altium already because I'm spending so much time in KiCad right now. I should use that to get practice, Altium practice, especially with copying the footprints. This is a little bit more difficult in KiCad. Especially, yeah, I have like to place each individual component, and this is only like one row of the supercluster. And I had the problem that one controlling MCU. Okay, people who are new probably are interested in Where is it? That's the excavator fund. Let me show it here on shape. So I have 65 PCBs, which have on the PCB there are 32 rows of MCUs, and on the side each row has 32 MCUs in. 65, 64. Oh shit. Yeah, I meant 64. You see, my brain is very mushy today. Brain fog. Let me log in. And I had the issue that I want signaling. We talked about like my bus idea to use like 32 chip select, that you can see them here, the chip selects. Can I zoom in? Yeah, we have 32 chip selects, and they are conveniently on two registers, because each of the registers only supports 16 GPIOs. And what I wanted is like to have the possibility to have a downstream, like receiving the clock and using the chip select stream what? Sorry. Okay, maybe let me explain it again in Paint. Gesundheit, ja, danke schön. Here we go. A strich stärker so you can see better. Okay, so we have the controller, and then we have, let's do only like 4 MCUs at the same time, yeah? Okay, so we have the SPI bus, that's the SPI that's connected to all of them. So we have, that is clock and MOSI. MOSI stands for master out, slave in. MOSI and MISA. Yeah, but the chip extender, Ulis, will not work with my idea, and it has if you like the clock on that is limited. I think that was also another suggestion from the engineering team. The clock frequency of the SPI to the chip, or is it I2C, is limited. So I will show you what I really want to do. So we have this line, and we have like individual, or the 3 lines here, and then we have an individual chip select. So this is, if you do it like with a GPIO expander, whatever, but you need, consider that each of those, we have 2000 of the master CPUs, so we have 2000 total rows. Here you go. So this is like 1 row of 32 MCUs, and that plugs into 64 slots here, and each are 32 MCUs. So we need like, this is 2000 this is 2000 48 times. So if we add like one component that costs like 50 cents, that's $1,000 more to spend for that. And these are in total, okay, these are the total numbers. This is 6 or 2 to the power of 16 MCUs. Anyways, these are the chip selects, CS. So we have like an individual line. In my design, we have an individual line to the slave. I would say it's host and client. A little bit of wokeness here. So we have like one host and 32 clients. What we can do, we can switch to a different mode where the host is like, we have like SPI mode. So this is SPI mode. And then we have the parallel in mode. I call it parallel pin mode. There's probably a professional, this is not a new invention. Most probably it's just, I don't know what it is, but what we do is we switch to the mode. So the host indicates, oh, let's switch to the mode. It sends like with Mozi, it sends out, okay, mode switching. And then in this mode, what happens is SPI is turned off. The clock remains. The host clock remains. So we have only then the clock. See, okay. Maybe we can also use like Mozi as an indicator to start or whatever. That's like details, because we have like 2 additional lines. And then all of the MCUs send a stream of data at once. So they're using, like in this direction, they're using the chip select line, since this is like a regular GPIO as well. You can just shift out like bit bang. Unfortunately, there is no, like, on the MCUs are so weak, there is not like a specific SPI mode or that you could put on this individual pin. So we need to bit bang it, like 0 1 0 1 1 0 1 0 0 whatever, and this one does like 0 0 1 0 blah blah blah, and so on. What happens here, this one just reads in the GPIOs. That's 2 GPIO reads. So we have, in that case, it's PA and PC registers. So we have PA and PC, and we have a 32 bits that we store, that 32 bit that we store in the memory, and this is just sequentially like a table of data which needs to be unshifted at some point, but it's basically all the data from all the MCUs at the same clock frequency than the SPI is capable of. And that's our limits here. So we have some data here. However, we unscramble that's, I mean, this one this one works faster, not as fast, so it can do that on the fly. But while these are working and not shifting out the data, we can. This is the parallel in mode. It only works in one direction, or we can also broadcast in all the directions. But usually we could broadcast with SPI as well, because all of the clients can listen to Mozi, but there would be conflicts on Miso, and we don't want shorts on Miso. So if we switch, either we need then to enable a unidirectional mode that is like only listening, then we can broadcast also here. But I think the chip select, we can override the chip select in software. That's possible. So if we don't use chip select, we can just listen to Miso. Then we can broadcast over SPI as well. We can do open drain. I need a pull up on that then. So that would work. Yeah, the typical one is good that you say it. I probably add this to, yeah, I have it here. There are pull-ups actually. That's what I thought. And I have 50 hertz, 50 ohms series resistor for reflections potentially, but I also heard from engineer, yeah, that's not needed. Past bitluni not outsmarted is on par. Yeah, no, you know what? Who outsmarted? I delegated to ChatGPT. What could go wrong? And ChatGPT gave me like all the. There are quite some recommendations. Also, I had initially an in-series resistor on the Miso of each of the clients. So even in push-pull mode, if there's like a conflict on the Miso, that would not cause like a short on that one. But I had to remove it because it's too many components. You can see I had like two capacitors here, a bigger one and a smaller one, because we have an LED flashing. Signal is slower. Yeah, that's true. So that's why probably will populate initially that one. That's just for experimentation. I would probably populate it with 0 ohms or short it, just to see what is the highest speed that I can achieve. Okay, maybe it's not that bad that I recite everything that I did for like the whole week since last time I streamed, because there are quite many thoughts that I had since then. I mean, I still want to do this. That's why we have like this individual chip select here. We could also like hack it and do a software chip select, just using 5 lines and have no like decoder, so you can like demultiplex or multiplex from 5 lines to, but the components are way too expensive. But we could also just use 5 lines of the small MCU and then see, oh yeah, that's my index, and now I listen or I can talk or whatever. So there's like a 5-line chip select, but that would have like to have had to some sort of interrupt handling, and that's not fully in hardware. That would be like partially hardware, partially software implementation. So I don't want to go this route. Now the issue with SPI is the longer the bus, the lower the frequency that you can achieve. Will it play Doom? Yeah, it will have one processor per pixel. New ideas. I have new ideas. That's the best. Should I spoil it? Yeah. All right. So that's QVGA. We can do QVGA. So I'm planning. Brace yourself. Okay. So I'm planning the bus. We had bus calculations for I think 120 FPS or something. Okay. So I did the calculations. What do I need to achieve for bus rate to have like full VGA 640 by 480 in 60 frames per second. That in true color. That's what I would love to have. But then one MCU is shared across 4 pixels, which is more complicated, of course. But the bandwidth should support that. So I calculated the bandwidth for that was, let me not lie, let me check. I don't want to show my screen. Maybe something wrong there. Okay, here we go. Oh yeah, that's by the way the pin matching for the MCU. I don't know, I maybe showed it last time. It's so strange. Like the pin configuration is so terrible. Clock out, unfortunately, MCU is on the A register, and then we have C, and I need like 2 SPIs, one downstream to the small cores and one upstream to the parent of that. So I checked all the matchings of the GPIOs that you can do. There are 3 peripherals, and unfortunately, first one is here. Then USB, we can't use the USB, but there are 2. That's the normal USB, but there is the high-speed USB, which is on port B. And fortunately, we have SPI 3 is on B. Also, SPI 2 is on B. We could also remap SPI 1 on B as well. The strange thing is the chip select. So if we if we want use SPI 1 or SPI 3 as like the slave, we couldn't do it because the chip select is on A15 for some odd reason. So A15 is used in those cases, but we are lucky SPI2 has the chip select on B12. In that case, this will be our slave SPI, which has the chip hardware chip select. So everything runs in hardware here, and we will, since we don't need like extra configuration for SP1 remapping, we just use SPA3 for the downstream. And on my testing board, I can use also the USB peripheral high speed or full speed USB for testing is also mapped on B. So yeah, what is this? Yeah, that's the remapping of that. So we were really fortunate with that one. The only thing is that programming the little MCUs, or no, programming this one, where is it? We have a CAN bus. CAN bus is unfortunately too slow. It's only 1 megabits per second. Yeah, here. The programming pin is IO clock. I don't know if you can still use USB programming with the second USB device. I don't think the bootloader would support it. I would need to test that. but we can program it once, and yeah, they have like to deal with the the chip selects have to deal with what's coming in there. All right, so we are lucky there. Do I have the stream? Oh yeah, that was our calculation, and what I had is if we calculate like if we use like our little MCU 1 pixel and or like 1 pixel, that would be 60 frames per second, so we need 60 bytes times 3, so true color, that's 180 bytes per second. That's not much. Times 8, that's 1.4 kilobits per second. If we want like a VGA resolution, whoops, then we multiply it by 4. That's 5 to 6 kilobits per second that we need to do. Yeah, it's not bad. The issues start like with the next level, which needs to like do 30 yeah, we can hear it. So the next level needs to operate at 200 kilobits per second, and that will be also SPI, unfortunately. And we have we can do the same thing with the 32 parallel downstream whatevers, but after that, like the level after that, we have 64 is already 12 megabits per second. And these 12 megabits per second are going from... Oh no, they are coming in... Wait, where is it? Okay, so we have... No, 12 megabits are coming in here, and then we need to communicate that. Is this right? Did I miss something? 12 meg... Wait a second. That can't be true. My calculations is off. 60 times 3, 180. Y times 8 times 8. Oh yeah, bits. Why is it times 4? Oh no, there is huh? There is 1 times 8 missing. Here, 100 megabits. This is the bandwidth that we need for VGA resolution and true color. Yeah, this was wrong. Damn it. Let's do the calculation here. Okay, so we have this level 3. This is what we have. This is not like we won't be able to use. That's megabytes. Okay, that will be enough, barely enough to stream over USB 3. But we have here, this is, let's say, QVGA. QVGA, this is VGA. This is basically let's do it 60 times 3 times 8. That's bits per second. Okay. Oops. Okay, and this is basically that times 4. So So this equals times 32. That's this level, and this is 64. 64, okay. So, oh, okay, and this is divided by 8, that's already, okay, 100,000, QVGA is 100,000 bits per second, and QVGA in VGA is 4 times as much, which is 400. So actually what we can do, that's the maximum is 450, so megabytes per second. We can do actually 8 times VGA resolution with USB 3. But how about no, we can do 4K. If we can do 8 times, that's 4 by 4. No, 8 times is wide angle 4 by 2 VGAs. That's let me maybe it is 4K. 4K. How many pixels is 4K? Oh, 480. It's not. Oh no, that's not 4K. 4K is huge. Times 4. Yeah. Oh, what? In HDR. Oh no. Hey, Kaspar. Here, Kaspar, I have some old tea. Yeah, that's a lot. That's a lot. That's... What is the bandwidth for a... Okay, so let's calculate the 4K bandwidth that we need. Foo! Hello and thank you. All right, so bandwidth, what do you say is equals 829440 excavator fund. Is it excavator fund or is it Christmas fund? Wait, I need to check. Okay, we do times 30. Do we do 10 bits? Is it KTR? Is it 10 bit? Is 10 bit enough or 12 bits? Should we future proof 12 bit? Okay, so this is the bandwidth. The bandwidth for 4K. Now we need 120 frames per second, and this is what we. This is the bandwidth that we need. It doesn't fit on screen anymore. This is the bandwidth that we need. 12 bit. Okay. 12 bit HDR or 8 to dig the channel. This project will pay for the final excavator bump. Trust me. You are talking about NVIDIA card or microcontroller. We just need the bandwidth. The bandwidth is the crucial thing. If we can resolve that, we know what we need. What we need here: 12K HDR and 120 FPS. Okay, this is the bandwidth. I can't count. Okay, So this equals that divided by 64. This equals that divided by 32. And this equals that divided by 32. Okay, so we just need half a megabit per second from the smaller MCUs, which will be only achievable 20 megabits if we use SPI is already a stretch. If we ask, like, get the data from each individual MCU. So the parallel downstream mode might be more suitable to get the data, but the issue is we need to switch the modes constantly. Sending only 36 bits, this is already a stretch, but we are also limited here. We can't transfer the data to a screen or to the PC. What is this, by the way? Sum. What kind of sum is this? P3 to P20. Oh yeah. Okay, let's whatever. Yeah. That's a lot, huh? But here it comes, peeps. I'm wondering yeah, okay. Next thing is 20 megabits per second. This would be the upstream that is barely achievable on this level, and on this level we are already stuck. We can never transfer as many like 500 megabits per second from like all the cards to that. So this is like I don't know what kind of black magic this would be. 600 megabits. This is insane. How is that even working? Okay, but yeah, like until, if we look at that, we get all the data from this, the data for 8K 12-bit 120 FPS from here to there is possible. From here, from all to here, it's possible, but then getting through the port to the main MCU somewhere here is not achievable anymore. We can't do 500 megabits per second here. This one is even only clocked with 144 megahertz. So how do you transfer that much data? It's not possible. Unless we put like a beefy MCU, but then we need like a TMDS connection here. TMDS signal here. We can put a beefy MCU on here because this would be... The issue is yeah, once we made this PCB, there is no way around like this MCU. We can't swap it after the fact. The only thing that we could do, we could also route the SPI through here and then do like interface magic, like replace the main board here or whatever, if we want like to. Yeah, that's what, like quarter of a terabit, that's basically almost does this here, what we calculated. No, wait. That's 35 terabits. What? How did we get here? Okay, we can with our bandwidth, we can do maybe HD. Let's move that over. Let's assume we can do maybe 20 megabits, no, 20 megabits upstream on this level. Wait, this will be a SPI bus, 20 megabits times 32. I'm lost. If we have like the perfect impedance matched, this is what we can do. $64. Yeah. The bottleneck is actually between oh yeah, the bottleneck is between this MCU and the main MCU, because we can achieve like 20 megabits per second times 32, which no, it will be already here, because this here maybe not 20, but let's assume we can do 1 megabits per second. This is like 20 centimeters in length. This is also the limiting factor. I try to keep this length as short as possible. This is like 20 centimeters, and this will be over 20, 22 as it's here, but I tried to route this. It's not possible. Even with 6-layer PCBs, if I do impedance matching, I will show you all the details in a minute. It's not possible to have all the chip select lines in this size. We are confined in width of the PCB, and also in a height we can do longer, but then this bandwidth will be limited then. So let's calculate the actual what is pixels, how many pixels. Regular HD is 920 times 1080 times 8 times 3. Oh wait, times 60. That's a regular. Equals that. Oh, AI learned it. Equals, yeah. All right. Didn't learn this one. Okay, so we need 45 kilobits per second from the little MCUs. Then we need 1.4. This is achievable. 46 megabits is already a stretch, but we could do HD with that one. And on the output side, we have 3 gigabits, but we can do, let's calculate it in bytes. 370. We can output this on USB theoretically, because we have 450 megabytes per second theoretically. It will be more or less 60 frames per second in 4K non-HDR content. But what else we can do? We can, now it comes, the Shipu, are you listening? I thought, if this is a graphics card, why are we communicating with the PC? Why? Why are we communicating with the PC? Petacluster. Yeah. So how about, let's say this is the cluster. I don't know, maybe let's look at, let me draw it like this. Oh, how do I scroll here? Okay. Okay, this is our cluster. Let's draw it this way around. Oh, now it's janky. Like with all the cards, they're calculating. They're calculating stuff. And glowing and whatnot, and there is like, I don't know, power input, AC power input with PSUs, whatever we need there, like some cooling or whatever that's needed, like vents. Then there is a USB-C port. USB-C port. And how about we add a VGA port here? Oh wait. No, I won't make it expensive, because the ones that I will use most probably would never see the day of light. They're on silicon, they're only on the wafer, and will be, they're basically one non-working prototype that will be packed up in QFNs just for this project. Okay, so I thought, I mean, maybe everything we did in the past led to this moment. Maybe also composite. DVI, maybe, but yeah, we could like use DVI on HDMI. Oh wait, we can easily do that with our Tang Nano 20Ks. Okay, let's do HDMI as well, but HDMI doesn't have a lot of class. HDMI. And then, what else can we do with the VGA? The split port, yeah. How about this was the idea. Now that Sonic is always pitching. In this case, it was KTR, HDR. No, Sonic was HDR. Okay, Sonic is always HDR. So how about we use like our we use 12-bit DACs. How about that? This will work on CRTs. 16-bit DACs. We could do it. I don't know what's do a suggestion for a peripheral. High speed. Dr. T-Man. Target is that's what we calculated here. We calculated like realistic would be like VGA in 120. This is regular VGA, 60 FPS. HD also 60 FPS is basically the theoretical limit of everything. But we can do anything like HD ready or 720p. We can do like 120 FPS or something. Sound output, yeah, that's another thing that I was talking about. We want, like the sound that we get when we turn on a nuclear reactor and we see the Cherenkov radiation. There are like some videos around on the webs. You can watch that. There is always like a clicking sound and like when we turn it on, we want some like deep hum or something. LCD 40 pin out. So how about, okay, theoretically, little coil wine. Yeah, we will get that for free with the 3000 watts that we will consume here. Theoretically, CRTs if they are really analog, they are HDR. They are not like very bright, but they can do actual like display that. And if you they have like a mask, but you could do like infinite horizontal resolution. So we could actually have like a super high resolution on a CRT in 16 bit per pixel directly from here. So we don't need to go. Yes. Yeah, 100 candela. Yeah, but I mean HDR, it's not like we don't want like Dolby Vision or whatever, or I mean the HDR, what was the HDR 400 or this specs, like the norms. We want just high definition, means that we have many levels of this color component. So just the color resolution, so we can advertise with a catchy thumbnail on YouTube. 16 CRT ran with 16-bit per, like 48-bit color HDR directly from this port here. And we can, this way we can avoid this limit as well, 40 megabits per second. We could distribute like on the main board. Whatever this main board is here, we only need to like pay once for that, not 64 times. So designing these ones here is more crucial than the main board. Main board can be always swapped and play around with or whatever. Only on monochrome CRTs. The Shippo what is only on monochrome CRTs. The other ones are... Oh, you mean like the horizontal resolution? Yes, you're right, because you have like the color mask. Yeah. Yeah, so actually, yeah, that's true. We can do... It's not that... That's also a good thing. We can consider like a super high resolution on black and white composite video. By the way, I have black and white, like this CRT here. This one here is black and white. We could run this in theoretically infinite horizontal resolution. Impedance. No, the impedance is important here. We have a limited green over. Standard VGA is limited. Oh, there are different modes. I think there are specs, like there are VESA specs to really high modes, but this depends on the screen. Okay, let me check that one, that component. But this idea is new, adding VGA directly, since this is a graphics card. Here we go. Let's see. Yeah, triple 8-bit DAX. Let's look. Oh, Mauser. (16-bit). There are 32-bit DAX? What? All right. Oh, okay. 1.3 megasamples. Oh, we need a lot of megasamples. Shoot. Okay, let me sort. Okay, here we go. Let's take. Okay, I switch to 16-bit and sampling rate 500 samples a second. 500 bucks. All right. What is this? Okay. 12 gigs per second. This is like, this is really VGA HDR. What do we need again? Here, calculations. HDR, that's Retina display. Yeah, we need like 1 gigasample. No, that's bits. Oh, wait. That's bytes per second. That's basically the resolution, the sampling rate that we need. HD in multiple gigasamples. Okay, let's limit the by cost or in stock. There won't be many in stock. They're very specialized. Oh no, they are in stock actually. Wow, probably that's how they make the actual money. How do I limit by cost? Price by quantity, let's say. Does it do anything? No, what is this? Okay, let's scroll down until we see something that's actually 4 channel, 1 channel, 6. This is crazy. What kind of... Look, it's QFN. Maxwell. Oh, 500 megasamples per second. Parallel in 3.3 volts, digital supply voltage. Okay. Oh, what is this? 63 2 channels. $30 per piece. Okay, yeah, but we are now in slow. That's 25 megasamples per second is basically VGA. (16-bit VGA). This would be for 14. Yeah. Generalgeschmack, hello. 200 megasamples, 2 channel, but there are no 3 or 4 channel. If we can save, yeah, okay, but it's possible to get a deck like that. Let me check what kind of deck we get from this one here. Oh no, this is only the data sheet. Not the reference manual. Okay, let's see. ADC 12-bit decks. We get 2 groups of 12-bit decks. So they are built in here, that one. But only like, well, what is this? Yeah, I can't character specifications. Let me check if I can find. Here, reference manual. Oh, that's why we... Yeah, they changed from the ESP, the original one had a good deck, but was very sensitive, and they swapped like from the S2, they swapped it to like what is this? Not a parallel one. It's now like a sequential or something. Basically, like a filtered sigma delta or something. But don't take my word for it. Here, DAX. Let's check. Ah, oh, aha. Ah, my Chinese is a little bit rusty. So let me translate it here. The features. If we can see anything about yeah, I should install Duolingo then. Triangle wave and noise waveform generator. Huh? Support DMA function. What is the maximum speed? Oh, what is DHR? What does that mean? What is a DHR? Yeah, I should. DHR. What is DHR? Okay, I will ask chat. Digital high resolution. Data holding register. Oh yeah, that's right. Oh. Pop. 12 bits. Oi. Okay, this is the configuration register. Okay, let's check. Wave reserve. just need like the DMA mode. Need to find, oh no, I don't see anything about the DMA mode here. Yeah, probably. There is the DMA function. Okay. I just need to find what's prescaler we can select on that. If we can actually, like, I mean, the bus is probably limited to 100 megahertz or something. System internally includes a triangle wave for triggering event. I have no clue. Can't find the information. Can't find the information here. Anyways, sidetracking stuff again here. Yeah, so my that's nice. Oh yeah, another thing. Slow by a factor of 1000. Yeah, all right. If we do air cooling, why don't we use a huge speaker for the air cooling? Hear me out. We use like a speaker of the size 50 centimeters cone. No, something smaller. And then we have a membrane that makes it like a vent or something. So we can send a bus wave that will pump. No fan. We will use like actual sound wave to propel the air. Just like we have a Blasebalg. Bladder. Here. Oh, bellows. Okay, here we go. Yeah, so like that, but with a huge speaker. We just need like this vent. Here is the speaker attached more or less. Instead of this cavity, we have this valve. Speaker, and there is, let's say, here is an opening, and there is just a flap, silicone flap. If we push in that direction, air moves in, and we can use that Bassreflexrohr, and we use that also connected to the main lever to amplifier, and use actual sound to cool it. What is this? Oh, you found it! Nice. I need this stupid. Yeah, when we turn it on, it has to do some sound, so we need at least some sound engine. Soundcheck just has enough oomph. But the membrane has to be so like fast that it actually works. Okay, let me save that. New sheet. Okay, reference. No, that's the data sheet that you found. That's not what I'm looking for. I'm looking for the reference. Oh, yeah, that's not only in Chinese. The reference manual is only in Chinese. I have the datasheet in English already. All right. Now here comes the issue. What we need is, where is it? The fuck, where is it? Let's remove that. Where did I open? Here. Here we go. Okay. So we have a limited space here. Whoop. And here, whoop, or yeah, limited space in this direction for sure. This direction we can get longer, but then these MCUs need. If we go to this design, let's take a look at the footprint here. These are 12 millimeters without anything connected to the pins on the outside here. So what I figured is the maximum space that we can. This is like 5.4 by 8 millimeters, and then I had the issue. How do I put 32 chip select lines through a slice like that's this wide? And I tried, okay, 4-layer PCBs are standard, cheap, whatever. And I tried to figure out a way to route that. This is already like design number whatever, or the try that I couldn't figure out a way, because we have we need vias, and the vias are penetrating through all layers. So when there is a via, there is only one signal going in the horizontal way that's possible. Otherwise, we would like to route around. And we don't want that on impedance matched lines like SPI, MOSI, MISO, whatever. So we have 32 plus like the SPI lines, and they need like perfect impedance matching to achieve like the highest possible frequency. So the new idea that I came across after trying that, I extended it to 10 millimeters in height, still didn't work. Like this was 10, still didn't work. I increased the layer count and tried some few tricks to get impedance matched, like perfect impedance matched lines while having like densely populated middle layers, and didn't work, especially not with 32 lines. I had some on the surface, like on the first layer. Bottom layer will be for power exclusively, so I won't put there anything except power, and maybe short like bridges within this here, because we have still like the LED here. This is the LED, RGB LED, and the 3 resistors that we really need, because if something happens, the power that this will, I don't know if it will brown out. We will have probably a separate power supply for the LEDs. For sure we will have that. But there might be common occurrence that we get stuck or whatever, and the LED will burn out, because we have like red is lower voltage than blue, and we will supply only, because we have common anode here. We need to supply like 1 voltage to all of those, unless we want negative voltages. If you can find Aben Mila, hello. Thanks for the sub. So we have, unless you can find this RGB LED and this 1x1 millimeter with common cathode, we can't do anything about this but supplying 1 voltage and then limiting the current. Yeah, I'm feeling a little bit stressed, because the giant project that I'm working on right now is hard. It's like hard on many levels, because like the ones before, like the clusters that I did. Where's the one? This one here. I did nothing like about caring about the speed, the layout of the buses and whatnot, and they were always struggling. And now I have a project that is so expensive, and well, the $15,000 to make it, and I can't bust it. So it needs to be tested and planned correctly so everything is worked out. And that's where we are right now. I'm trying to have this fast bus while I'm constricted to a small space, like 5.5 by 8 millimeters, rather 5.4, so I have more space on the side for the controlling MCU. So yeah, long story short, or long story long, I tried to get all the chip select lines underneath that, and also the, like you can see it would look like that. So we have how is it called? We can see that in KiCad, the project, the calculator here. You can do calculations on impedance matching, and we like to match for 50 ohms. So if you look at that, that's a strip line which has a top and a bottom reference layer. Reference layer ground in this case. It could be also 5 volts or 3.3 volts. I think, but ground is a better choice because I think it's more stable, I suppose, than the power layers. Anyways, strip line would be one alternative. So the width, the only thing that matters for the impedance here a different but similar, yeah, DFN package of is a little bit smaller, but the problem is we don't have GPIOs like PWMs for LEDs and so on. Prototype would be different, but so yeah, the problem, I have several issues with the routing. I will show you that. Yeah, that's what we are doing. Yeah, in KiCad you can just calculate more or less, but I will show you a better tool than KiCad. So you can do strip line, which is cool. If you have, let's say, on 4 layers, this is already weird because you have like the stack up is you have on 4 layer setups you have a very very thin dielectric between the 2 layers on top and on the bottom, and in the center you have a very thick core. So actually the height is here, the total height, but the distance A is way smaller than the total height. So it's a little bit off, but you can calculate that here, and then you can play around. Okay, what width if I have this configuration? So let's say we use a 6-layer board, and we use like inner layers that sandwich all the signal lines. That would be perfect, except like if we have a signal line next to it, we have like some sort of crosstalk. That will still happen. So in my opinion, that doesn't show the coplanar with ground plane. So what I'm doing is something similar to that, but I have also a ground plane on top of that. So this is matched for 5396. What is I don't, do I have the height? Yeah. So you can do this, and it's 0.1 millimeters. That's the lowest you can go on JLC. The distance to the ground, and this will more or less look like here. Wait, let me update that. Oh, here. This is what it would look like. We need like whenever so basically the ground on top or next to it the biggest issue is that I have right now is that specified on JLC is PCB toolkit by Saturn. Yeah, I will use Altium in the end anyways for the final project. That's what is basically also paying for it. And I have like the access. But what I like to do is test, just play around and test like for the prototypes how it will look like. So my issue right now is that the biggest issue is I could place them way closer to each other. So we have a ground that's only like 100 micrometers wide, and have the clock lines. These are by the way, they are not 1.5 millimeters thick. They are 1.2, something very specific. Yeah, all right. So the issue that I have right now is that the vias that we need for connecting the grounds and also for taking out the signal to each of the individual MCUs, they have a hole to copper distance, minimum distance is 0.2 millimeters. And that adds up to be, wait a second, isn't that still too wide? Oh yeah, in that case, what I'm using is, no, this is still too wide. I'm not sure if I'm not wrong here. Why did I pick this? Oh yeah, the issue is the ground via. That has also 200 we could like bend this one, but we need to avoid any like kinks or whatever in the line to have like a perfect signal. So this distance from the ground via here to the copper of the signal line is what adds up to this whole thing. Otherwise we could like make it more narrow. But there is like so my idea was to make the signal lines to pack it like more signal lines like that. You can see, okay, these are way closer together, but they don't have any, oh wait, this is outside of our, change that so it will be included. So they are closer together, but we don't access the lines here, so we don't need any vias. Oh, don't look at that's not all clock. I just copied the line, but we need the ground vias only there where we have the path that's going back. So actually it's like two lines. We have the signal, and then the ground needs like the same length more or less to go back on all sides of that wire. So top, bottom plane, and left and right from that. So we need at least the grounds like next to all of these here. One is missing, so we need also a ground here. Let me add this. Yeah. So on these sides, so we can't place anything else here. But you can see it here. Okay, let me remove that. On another layer, I have then two, and if you look close at that, between those we have ground, and between those we have ground. These layers are right next to each other. There's like this core in the center. Maybe I show it by, you pull that out a little bit. Okay, so on the stack up, oh, this is back copper, this is ground plane, this is ground plane, and these are the two signal layers. They're right in the center, they're next to each other, but I staggered them this way, so this here also acts like a ground to this line here. So we have, let me show that in Paint. So let me zoom in here. This will be the 6-layer stack up. There is some stuff going on the top bottom layer. So here's the power. Here is the components. Then we have ground. Then we have ground, signal, ground, signal, ground, signal. And then, okay, maybe I should make it closer. Like that. Okay, let's draw. And on this side I have ground. I don't know if that will work. Ground, signal, ground. We have really densely packed, or as dense as it is possible here, the lines, and then we have like SPI, which is basically only ground, because that has, yeah, somewhat like that. We have the vias here. So these are the ones that are attached, and then whenever this will be just chip selects. Whenever it's turn for this chip select, it will be just routed to the chip select ingestion here. Which is on the top here because that's the first one, but I need to remove that as well. So that was the plan for that. Still, I had issues to fit 32 in the small space. As you can see, there is not much space here. That's like 8 millimeters by 5.4, and unfortunately, these don't have internal clock, so I need to supply also the chip clock. Like I will use just a PWM from the main MCU here. I hope that works as a clock signal. So that is also another impedance matched line here that I put here. I wanted to put it, maybe I show it. Oops. Move. Let's move this one. What's faster than an escalator? Here. I show you the physical limit at what we can do. Oops. That's good. Okay, so yeah. Control plus T. Oh. Of what? Of the current selected component or what? No, I don't use that. Oh, this is Foo. Holy Flame, that's also cool. Selected part. Yeah, but what did I do like with individual components? I mean, I have like all the components here that are repeating. How do I arrange them? So what I'm currently doing is I'm very pedantic about stuff. I want for project instances, it allows to create a module as if it was a separate project and replicate. Oh, foo, how do you do that? I know that like, do you do like a PCB design and then place the PCB design as a component, or is it like a multi-part component, or how do you make that? Because I would like this once I have like the arrangement of the MCU, I would like to just repeat it. Currently, what I'm doing is I'm on this one. I mean, this is just a prototype for testing. I'm doing it like that. I take that. I have my grid here, 5.4 by. Oh yeah, I know that. That's copying the tracks. That's what I do as well. But what I do is I take set the origin for that, and then I would take like the MCU here, and then here. I just need to find the center, which is here. Okay, so now we're basically on our grid. I can move the components around. I just whatever grid I like to place them at. So this is how I do it, but yeah, I have also the grid for the distances of signals and so on. I just need to place my origin at the corner of the signal, and now I can place those exactly. It will snap to the distance that is for my. That's how I do it my way. But if you count, okay, now we are here. If you count the lines that we can use, like chip select lines, it's still short. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We are 2 signals short on this one here. And there is another problem. Okay, we left some space here for routing the power to the LED, for routing this one here. Wait, this we don't need to route that actually. We can place this component on top of here. This via goes away. We can route that. Let's say we do it like that. We still have the issue is here. The clock is here. Now we can't get like even we need the resistors first. So we have a good space for the resistors here, maybe. Let's say the resistors will fit. Also quite interesting, if you want JC assembly, the distance between the component and any other component like QFN and any other component is 1 millimeter. What? Yeah, I ignored it here. I tell you why in a second. So yeah, we have the issue right now. Oh wait, we can. Yeah, but this will be. Our clock will be cross-talked by the LEDs. Now we are destroying basically our LEDs, our clock signal with the LED PWMs, which is terrible. But that would be an alternative. Let me check that. What? Why is it flipping around? I don't know why. Okay. And also, I think, okay, we could route this like that. Let's say this, but we are still falling to signal short. I don't know if I want to like affect the clock, but this is something that we can actually do. There is not enough, there is no space for ground around that one here. We just hope that the ground beneath that is closer than the resistor. Especially, this will affect this clock. If all the LEDs have this same pulse PWM on the LEDs, it will affect the clock for sure. Yeah, so this is an issue. I show you why I place it like that. So for my, if you look at that here, I used a trick. I thought, okay, I can't place 32 lines in this confined space, even with my staggering trick here. Is not enough because we have like some space that we can share. There are not buried vias or whatever that we can use. But what we can do, we can share the clock and share the SPI lines with two MCUs next to each other. So the idea is now the MCU will control half a line of 16 MCUs each, and we place the same MCU on the other side that does the other half. So we have like this is half of this one is controlling half of two lines, and this one half of two lines. So we don't need like to put two MCUs like next to each other and try to route it, or on the back side which wouldn't fit because we don't have enough space on the PCB. I can show you that. So this is why the newest layout looks like that. I think the linear pattern here. This pattern is, I think, it's 8 millimeters line distance. So we have 16 millimeters between each of the MCUs. So we have like 3 millimeters extra space between the footprint of each of these MCUs, which is cool. That resolves many issues. We are able to share the SPI lines that are shared anyways between two of those MCUs. Then we are also able to share the clock line on the other side. Unfortunately, there's no way of routing that. Like, we could shorten the pins here, maybe route it this way to the center. That would solve an issue. We can do that because the clock. Oh, we can share the clock. The next lines have a different MCU, different clock. Okay, yeah. So we need to change the footprint here. So Thea, when I was meeting Patrick in Hamburg, Patrick from WCH, talking about, Thea joined us in the restaurant, and we are talking about stuff. And Thea told me back then that she basically buys the standards for footprint layouts, reflowing, and whatever, like all this engineering around surface mount components and routing or whatnot. And she told me that the pads for MCUs, they're all too big. They should be almost exactly what the pads are on the chip itself. That's like the new how you call it, like the new way of designing that. So these pads are way too big. We can actually maybe route the clock somewhere here. It will be still like noisy. Making it for hobbyists. If you want to, if you want to saw that by hand, it will be harder. But I don't think I have currently most of the time with the QFNs with these footprints. I have the issue that my paste is too much, and I get like shorts or whatever. Not on these ones, but on other ones I have like shorts, or especially on these here. These are the quad flat packs. I have many like bridges, and they are hard to come by. So on quad flat packs, if they are shorter, there's less space that could like smudge or whatever. I don't know. Especially underneath them, if you have a long pad underneath the leg of the quad flat pack, there will be a big like drop of solder that you can't get out by just like putting a lot of flux and so on. You need like to take some wick on top of it and try to get it out. So this is actually harder to have like two big pads here. I don't know if it's like necessary to have the pads big like that for like adjustment, because the paste adjusts the chips. So if there is a lower precision in by the pick and place machine or whatever, that might help. Not sure. But the new paradigm is that to make the pads smaller as of here. Let me check that. I don't want to like expose any open chats. Here. Maybe I'll show that. This is what she sent me. Bottom only. It's quite hard for me to get this round, flattened J heads, I heads, but I toe side heel. 100%. Wait, where is it? Side, toe heel, P termination. Okay, so these are basically, I think 100. Where is it? 100% is just matching. Where are we? Bottom only chip. Here, 1:1 lens size. Toe side optional is 50 micrometers. So actually if we look at that, inspection will be harder if we have like paste only on the bottom, because on my when I rework them, like on here, let me turn on the camera so I can show. Oh wait, we can look at the microscope. We turn it. What? Stencil printers for 40 euros? What? Okay, let me turn on the microscope. So where is it? Okay, so if we look at okay, so basically, especially when I reflow, this is not done by me, but you can see like this extra solder to the sides that is going up the chip, and that's a good indicator if you have a cold solder joint or not. So when I do the pads, when I make them smaller, especially on the side, I won't be able to inspect that correctly unless I'm using I mean, it's JLC probably will complain, but if I like to reflow them here and rework, yeah, I won't be able to see that because I don't have like X-ray or whatever. So you can check that with X-ray inspection. Yeah, not sure about that, but that would be one way of maybe getting the clock from here to there and get one line more here. So we can't, we will have enough space on 16 millimeters actually, because I was right about to, it's good to talk about, like it's like rubber ducky development, trying to explain everything and then see what my possibilities or errors are. And actually it would be an error to share the clock, because that's different, completely different to new set of, like this row would be completely different to this row. So we need to put the clock on here, and instead of putting, since you can see the frame is going here in the center, instead of putting 3 lines here, we need to put 4 lines here, including the clock. For this MCU, I have MCUs that don't use, like they don't need external clock. They have internal RC oscillator, which is way better, but I don't have enough of those chips. I requested them. We have even like once more space here, and we can place all of that here will be the signal lines leading up to the chip select in here, ingestion here. So this one will go away as well, because we need ground here and here next to chip select. These two will go away, or this one will be basically ending. Yeah, I'm on a different marker here, like that. And I tell you now is the interesting part. Let's remove that. Oh yeah. This is wrong. Why am I still here? Huh. No, that's right. Okay. Yeah, this needs to move around somehow. This one is... Oh, yeah, we are the wrong layer. That is okay, that will work. Okay, and this is like a different signal, this CS17. This is CS16, which will go CS18. Yeah, they need to end up here. Here will be basically ground and ground. Now we have that. The only thing that will be missing is this clock here, which will be, oh no, clock needs to be to the center because it needs to go to this one and this one as well. So we will have actually quite a long clock line here across that, but there is no other way, communication here. The requirement for the signal of the clock is lower than the one for SPI. We don't need, like usual, if you use like an external oscillator, you also have like more of a sine wave than a square wave, and for SPI we need a square wave. So having these closer to the center, to the lines, is probably more crucial than this clock line here, especially as this chip might completely change and this clock line will be obsolete anyways. Yeah, so this will change. Interesting question. All right, so that might be working now. One interesting fact is I was asking myself, all right, if I have so many unpopulated pads here, can I use this here to route stuff? You could do it, but the issue is that if you remove those, first of all, it lowers the durability of that. So the chip, if you have like only 2 connections, the chip might just fall off. And then you need like a symmetric way of aligning everything. So since I have these here all populated, I also need all those here to be like populated. So I can't skip one of those 3 not used pins, because these are used. So that needs to be symmetric. What I could do is I could use remove that one and that one maybe, but yeah, that could work. It's symmetric, and we could route something in between there. Actually, not that bad. No, we can't place another resistor here. Yeah, I really don't want to do it because I don't want like the chip in placement to rotate or whatever. So this will be the last resort to just remove pads that are not needed or make them really, really tiny. But then it needs to be symmetrical. All right. Let me check what Thea is saying. Huh. Wait a second. Okay. Sorry. TI to make a package for you. They're getting crazy with their footprints. Sorry for the TI. Okay. This was that. we are solving many issues right now. If I can route the clock through here, that will work. Yeah, also one requirement that restricts me quite heavily is, oh, I'm not sure if we can even fit everything here. I hope we can. This one will go away. The problem is, yeah, we will need to move everything by one. The issue right now is I want this component and this component, the LED and the MCU, to be centered on their line. Like it has to look like centered and symmetric for each two lines. If we compare it here, I want it to look like that, not like the LED. Neither the LEDs nor the chips should be like shifted like closer to each other for a pair of lines. That's one restriction as well. So quite some restrictions here that I work with. But I think we found a workaround solution, maybe even. And this is where we start today. I think I need Knoppers to rejuvenate. Oh, one more thing. You're probably wondering, okay, why is this not 1.5 what we calculated in our impedance? Yeah, and there is a lot to learn and a lot of explanations. So the 2 hours, the 2 prior hours is quite informative, especially now we saw the progression from having SPI for 20 centimeters, now shorter, to an SPI of 10 centimeters. No. Booster is empty. And solving our issue with how many chip select lines we can fit there. So, where is this number coming from? We had our KiCad's impedance calculator here that was saying, by the way, thank you to chat who suggested that. Basically, we have more or less a calculation like that, or coplanar with. There is no strip line with coplanar here. But if we do like this, that gets worse. So it will be on this one will be more or less like maybe even 6 to match perfect 50. But the 50 is like a compromised number between whatever. There are like 2 properties that matter. We could go as low as 30 ohms or 80 up to 80 ohms, which I don't know in which way the signal will get worse, basically degrading in power transmission, like, and in signal like edge, or I don't know. I have no clue what I'm talking about here. Anyways, this calculator suggests 1.5, but there is another option. This is the last information that I discovered for you, my friends. Here we go. What is this? JLC PCB impedance calculator. you can select 6 layers, PCB thickness, classic or typical ounces, like 1 ounces top layer in a layer 0.5, which is the standard if you don't change it. And then if you do that, it will calculate 1.425. That's just single-ended non-coplanar. If we do coplanar single-ended and we say the top reference is layer 2, bottom reference is layer 4, signal reference is layer 3, so that's what we are doing. This is basically our top layer where you have our components. Then we have a very thin layer. Unfortunately, the thin layer is on the wrong side. Here is a thicker layer, but this is our ground plane, which is completely closed. Then we have our signal, then we have a thin one, and then we have like the other one, semi-signal, no wait, pre-break here, the other ground, which is the staggering of the other one. So hello Bahadiruddin. So they have the actual data here in JC to do that. So if we calculate coplanar single-ended, we get that. Oh wait, this is impedance match single-ended. We need to, oh yeah, here. Impedance trace to copper is 1 millimeter. Now we can 0.1 millimeter. And look at that. That's our trace width. Calculated by JIC specifically for, we can pick also like what kind of stack up we want. You can select that when you order a JIC. So you can basically take the exact impedance calculated here. I hope it works. We will find out in the end. Oh, red thumbs up stack up. Okay, let me check that. Which one is that? Oh yeah, look at that. Look at that price. 6 layer. That's only, yeah, this size. 1.6 single PCB. This is material type. Wait, epoxy filled capped. Oh yeah, I changed that. I'm using bigger vias because this adds massively to the cost. Only once you got like an extra engineering fee. But I have the impression like the difference between this and this is basically almost zero. And I guess we will have a better yield because we have thousands of vias on one PCB. Imagine like with the smallest size that's imaginable there will be breaking tools within one of the PCBs. So there will be a mess up somewhere. And we use like the smallest tool available. So I thought, okay, with this tool I think we are good with our current setup. It doesn't add a lot. Bilaterals, okay. Let me check what are you working there. Is it Turkish company for what? Oh, you're also manufacturing stuff. Okay, where's the impedance matching material? Here's, by the way, the different types. Where is the impedance matching? Oh yeah, here. Specify stack up. No requirement. Okay. Oh, and now we have. What are those here? What is best performance? Maybe we should pick that right now. Oh, wait a second. Oh. Oh no, we need something with thicker core. We need something with thicker ones here. Actually, this is better for our purpose. Best maker? First domestic and national factory. Can you order there? Just like a consumer style, a hobbyist style? Oh, this is also interesting. Wait, but I'm wondering if there is a stack up that would. If we would use, okay, this one is cool. 0.5. Okay, no, 0.5. We need thin ones between that here, and we would need like a thin one here. 0.6. 0.2, 0.5, 0.2, 0.4. Yeah, they are not. This is probably the best one for our purpose. We have a thick distance, but also the issue is to get our signal from the center of the PCB to the outer thing is already like almost to the chip is almost a millimeter added. No, we need to use 1.6 millimeters because we will attach it to basically an edge connector. Unless there is a better way of thin. I don't know. We can't use those connectors again. 0.8 millimeters. They will be too big. The PCB is already 30 centimeters long. 30 by 22 or something. So we can't do thinner ones. You know what? It's quite interesting. Let me go through the different stack ups and see what that's even smaller. That's even smaller. We can just pick the best impedance here. The smallest value. Look at that. We can just, oh wow. Can we remove that completely like that? Let's assume there is nothing. 1.5. 7628A. Oh wait, they have it in the calculator as well. Oh yeah, that's that one. 0.1 millimeters. That's interesting. We can use like a 0. Wait. If we use layer 4, or let's say layer 5, that will be that. 0. I think we can use 0.1 millimeter traces here with this stack up. That's not bad. This is 0.5 millimeter plus, yeah, 0.5. The distance is not bad. What else do we have? Oh yeah, that's terrible. .2. I think I found the best stack up here. That's interesting. So I will pick. Where's up? Yeah, here, this one. I need to be careful to order exactly this one here. 6, 6, 7, 6, 7. 8, 2, 6, 7. Okay, let's check. 8, 2, 8, 2, 6, 7. Confirm. Oh shit! That increased the cost. Maybe it's not that important to me. What are the different? Oh, they're all more expensive. Okay, wait. Board 38, color, material type. Yeah, the color is the issue. If we take black, if we take green, it's like $30 less. Wait, let's do my test. It will be 20 by, what is it, 16? No. 20 millimeters by 150, more or less. $170 just for the engineering fee, stack up fee. Do I have ENIC selected? It's so expensive. Plus minus, boom, impedance control. Plus minus 10%. Okay, required signal layer, reference layer, impedance type trace width and spacing, desired impedance layer and specific position of the impedance trace. Provide us information, JPEG or Excel format and included in the Gerber file. Process or engineers will adjust trace width to achieve your desired impedance. The confirm production file option will be automatically selected and shown. Yeah, I will do it myself in that case because I'm using their calculator, so I don't need the engineers to do it for me. What is this? Tinted, epoxy filled. Yeah, that doesn't matter because for filling they all need to be, the hole size needs to be bigger than 0.3, so there will be not filled. In-pad vias are basically bad in this case. So with the LED we need to be also careful because I think I have in-pad vias there. at least for the power. I might need to remove that. Oh wow, this is layer stack up, no requirement. Yeah, I need to put the requirement in there. $70 for the requirement. But you know what? It's really worth it to... Oh. These are not as expensive as... Oh, this one is expensive. Expensive. The first ones are not expensive. Maybe we can find something that's also acceptable here. Because we don't need like super thin traces now that we found our solution. I really wouldn't like to change it actually from what I have now because we figured it out. Or we can change it to a thinner trace. 0, yeah, that's bad. How did I calculate signal layer, coplanar single ended? No. Yeah, that's the coplanar single ended. How did we get here? How did I find the 1.0? Okay, that's 7628. That's our goal. 134. That's 2116. 2116. Oh, A or B. Wait. A. 116. Yeah, expensive. Oh wait, 1.7, 2.1. Yeah, no, I think we need to go the extra mile here. 1080B. 1080B. Let me check that. 1080B is also an option. Yeah, it's same. I think. What was our best one? Three, two, yeah, that one here. 6728A. 6728A. 6728A, this one here. Yeah, we need to take it. If we consider for the whole thing, like if this is 30 by 22, whatever, 22, oops, millimeters, oops, too big. And we need 70 boards, 75, 1267 just for the boards alone, with the hope that it works. If we do a single one, let's say 5 for testing, still $270. Alright. In January I'll get my budget. I hope I can squeeze them out, and up to 6 days to get it. But we have a new stack up. We have a winner, my friends. Winner, chicken dinner. What if we do this, then it's lower. Yeah, okay. We take this stack up. That's important. I need to get the information right. And now we can lower the value. That's cool. Tasks. Yeah, it's an expensive. But if you consider like if you have, oh wait, like main boards on computers like PCs, they have way more layers. It's just the amount, I believe. Once it's figured out, they could mass produce. I should do one design that's not impedance matched. Oh, it's also 6. Wow. How do you route so many, like if you have BGAs, how do you route all the signals out? How does that work? Okay, prototyping phase. Impedance matching. JLC stack up testing, and then I just want to copy the name of this. And 6 is power. Okay, I got my info here. I need to take care of that. This will be yeah. Wow, stack up the impedance matching here. Specify stack up. Crazy. Okay, we have a winner. New things learned, stack up selection to get a better impedance than this one here, 1.135. We need to select the stack up anyways, and we can achieve something that's better. I guess, let me check something else. If we can make it a little bit less expensive and yeah, 331. Yeah, but that won't work. 331. 3, yeah, this will be 17. 143313C. 331C. 33. This is D. No. Only A is this one. Oh, 3313 without any. It's probably C then. 1418. Oh, this is the standard stack up. Maybe we keep the standard stack up. It's not optimal because we have a thick layer here between. I'm wondering if all fabs can do that. Otherwise, we need to reroute everything. I'm worried. Pips, I'm worried that if we use that, or I will leave space for that stack up. We can pick another one. Let's leave it with that stack up for now. 3313. Even though it might have more crosstalk with the other lines, because we have the thin layer here and the thicker layer to the ground, to the actual good ground. But then we have also a shorter, there is another advantage or disadvantage. This layer thickness is, oh no, actually not. It's also 0.6. Yeah, I'm not sure. I'm not sure what to do right now. Let's keep it with the standard stack up. Or will I impedance match? It would be a nice thing to test. We can still change the thickness of the wires. Why is it moved like that? Okay. We can change the thickness maybe later of all of those here to 0.1 if we like. If we route with this thickness, with the standard stack up, and we can fit everything, and then change just change the thickness and refill the grounds, we will be fine. Let me get that here. Okay. Okay. Oops. 013. What is 113 or 1135? Ah. All right. I'm wondering if we could run tests with, that's maybe a project to test SPI, the maximum SPI speed that we can achieve with impedance matching, non-impedance matching, whatever. That's actually quite a cool project. Please remind me of that I don't forget it. I mean, this will be already a impedance matching thing. Whoops. All right. Now back to work. We will change the footprint here. I already changed this. The ground pad. I might increase the ground pad size, but What I'm wondering is if we can, yeah, make the pads shorter. So this size here, is anyone even listening? We have 3 millimeters. That's the actual size. So here on the manufacturer layer. Wait, that's the one. Basics 1 millimeter pad. Okay. Let's do file save as. Pads, shorter pads. Okay. All right. And we will consider, we will take the schematics here. This is what JDC uses. Package information, pin pitch, body size. 3 QFN20 is 3 by 3. And they don't show the pad size here. 0.2 millimeters. What width do we have here? 0.2. So that's actually matching. We don't have any specs on the pad length though. Don't see anything here. Yeah, it's QFN. So let me pad stack mode, normal, pad size X and Y. 0. It's almost 1 millimeter. That's heavy. Okay, let's take one of those chips and measure it. We have caliper. We have the actual QFNs. WCH QFNs. Let me check it out. Which one is it? Yeah, that one is alright. Oh, that's the bigger one. 6.8. Here we go. 6.7. Nope. Microscope time. Oh, nothing. Yeah. Doop doop doop. Uh-oh. Ah, that's quite tight here. Ah. Huh. That looks like yeah, it could fit. We can fit one in between. So I made the center pad smaller anyways. To be able to put stuff there, but we can shorter the pads, I believe. Let me turn it on and then measure the width. Oh, I don't believe I am very precise with this here. 26. Okay, interesting. 36. Something's between 26 and 36. Don't see it. Actually, I can't measure it properly with the calipers too. But if we look at the pad is 200 microns wide. I would say it's like twice the length here. So we might be at around pad size. We need to find the footprint. Wait. Take a look at this here. Okay. The pad size. Oh, we can maybe determine that a little bit at least. We have the pad size is 1.8. So we have a total of. Can we count the pixels? Yeah. I would assume that we fit one pad in between, like if we do that, and we can yeah, we can just take oops, let's leave it here. Okay, that would be too long. Yeah, 3.6. I would say it's 3.6. Okay. I mean 360 microns. So let's make the pads shorter. That would be 7.2. Doesn't even hurt, does it? No, wait, where's the center of the pad? Is it at 1.5? No, they positioned it at 1.45. If I place it 1.5, on the outside it's shorter, on the bottom it's exact. Can we even make it shorter like that? So we still have enough for some solder here. And we gain some space. Okay, I need somehow to set the center here more or less. So where are we? Okay. .47. Oh. Change the grid. Oops. Yeah. I'm wondering if this will be enough to route a signal in between the corners. That would be amazing. Also, we gain a little bit space outside of that. Oh, where do we end this one here? Shoot. Okay, X is at 147, so this one's 147, size 66. It's completely random here. Let me measure it. If we can get 0.3 here in between, then we are fine. Yes. Oh. We can't get ground, but we are fine. This is good. I like that. I like it, Picasso. So, who heard of the Great Reset on January the 1st? There won't be all the memes will be reset. So no more 6-7. And especially like I'm Gen X, so I like it. Picasso is more like Gen X humor already. 6-7 is Gen Alpha. Is there a new generation coming? Where are we right now? What's the Gen Z humor? Uh, 147. Okay, 147 minus 147 and 66. Bloop. Let's check it again. Okay. Game changing here. Everything will be game changing. This design, we finally found a solution. Yeah. I like the what? We like to joke in the Gen Z that we don't have the humor because we don't exist. You're also Gen X like I am. Yeah, you are older, but I'm just barely. I'm the last year of Gen X, so you still will fit in. You're not a baby boomer. anything before Gen X is baby boomer. Generation limits are, yeah, that's true. They're more tight. Like usually people get like in the early 20s pregnant, so there are probably 5 generations already since we were born. Wait. Yes. No. Yeah, they're not. Do people in Poland still get kids nowadays? How is it? Or is it like in Germany, nobody wants kids? Like me neither. I think not having kids, it's a little bit of, let's say, desire for comfort. Also, the climate for having kids isn't very nice. Yeah, you're Gen X. I knew it. Millennials start at 80s, and I'm born 79. So you're not 10 years older than me, are you? No, you're in the 50s, but not that much more than I am. Position. You are a year younger than me. You're born in 80s? Like, no, yeah, 1980? I thought you're... What? Okay, then you're almost you are almost a millennial then. Let me check that. Oh, you're the last year, like 1980 is, yeah, 81 starts. So what are the limits in Poland then? And I don't know, maybe you can clarify it. Why is it called Gen Y, Gen X, Millennial, and then starts all over again with Gen Z is like the last one, which are starting like year 2000. No, wait. Earlier, no, 2000s, and then we have a new generation. Random, pretty much random. Okay. Corner size here 6'6", 6'6" or 6'7". Oh wait, it should stop. 4766. I must concentrate. 4766. Okay, this is correct. With tornadoes. What do you mean with tornadoes? Well, what's... Yeah, true. Or wait far out. All names are made up. Yeah. That looks small. Okay, pips. I think we got it. Ah! Ah! You're right. How did we miss that? That would be a terrible mistake. Imagine that 65,000 times. This footprint will be etched 65,000 times. Ah! Alright. Thank you for noticing. What? Johnny! Bye bye! We did some education today. Was it 2? Oh, we had 3 hours. Okay, 1 hour left. We will do some routing, and yeah, I know, I'm tired like all day long already. Should consume fewer energy drinks. My concentration. Okay. Hey Quindor, how are you doing? Short pads. Okay, here we go. Update that. Yeah, that's good. Whoop! Look at that! Oh, that looks way more comfortable. Probably also increasing the signal integrity because we are not like having any lobes or whatever. Like having a big pads also messes with the signal integrity. Everything is bad. Oh, look at that. Clock signal. Yes! Woo! Whoop whoop. We can put it closer to here. Oh, there is even space for some ground in between here. The only close encounter is close to the pads. But here is even place for, if we put it next to the ground, that's cool. Scratch on the mark? Why? Oh, yeah, I mean. All of them, Kundar. We're changing to the new paradigm of footprints here. we're trying harder to be conform with what we need for actual quite good impedance here. So we are really trying hard to get the best out of our stuff here. Wait, where do we put clock? If the clock, yeah, it doesn't matter. One of those needs to be shifted. Yes, 6 late. Oh, you spotted it. All right. Clock needs to go away here. We don't have clock anymore. Oops. What do you mean track size per layer? Why? Why that? For impedance? Yeah, I don't know if I need like, I mean, we could. It's not like we are having a lot of impedance matching here. Yeah, I know. We did. Oh, you missed that part, but we are matching for this stack up. Yeah. So we are matching for that one. We're using single-ended with 2 reference planes, more or less. Yeah. Yeah. So I have this one. Okay, I could change the trace width for the top layer of this stack up. So let's trace single coplanar single-ended. No, in this case it will be only single-ended non-coplanar, and we have that, and this will be 1.56. What? So they need to be 1.56 on this layer while they're like almost 1. Okay, I need to put it on my 1.6 here. That's less of a problem than, but can I put 1.6565? Let's add it here. 0.1565, what was it? 1565, okay. Ok. Boop. Here we go. Impedance matched. And now the ground here. I can't be moved anymore. It's too close now. All right. Okay, I will just keep that one to remind me to adjust that. Thanks for the tip. I will take it. I take it. Now what we need to do is we need to move everything one row up here, but we need to zero that. Whoop. And signal rounded. All right. So we take, oh no. Single, make a screenshot. I don't know what you mean with screenshot. Yeah, for this one here. Yeah. We have also coplanar thing here. Yeah. We have a coplanar. I made it so here, and we have coplanar single-ended here, and this is one. This is what I use on the inner layers, and yeah, because I actually have those reference planes here. This is my design. So it gets really short on small on this one. We can even go down to 0.1 millimeters on a more expensive stack up, which is like these two planes closer together. This is a bad stack up, but it's the cheapest one. And I really don't want to pay $70 more just for an experiment. So I will keep the grade distance and then adjust the. Yeah, I will try to. Yeah, you know what? I will. What is the highest speed you were able to achieve with impedance matching signal SPI? Have you tested, like, what's the highest frequency? On what length of wire? But Ethernet is differential pair. How long were the traces, if I may ask? Okay. Yeah, because this will be 12 centimeters and I have another one with 20 centimeters going on. So I guess, like, if I can ever achieve 20 megahertz, that would be amazing. But I guess it won't happen. So yeah. Do you even need impedance matching on those lengths? Oh, you're right. You're right. You're right. Sandwiching that on 6 layers, like in between, is good choice then. Yeah, I don't need CE. Woo! Maybe we can do Bluetooth. just with SPI. Yeah, that's true. Yeah, that's what why not doing the actual product, selling actual products. But once you're scaling, that's, I guess you have a good living from that. What did I want to do? I wanted to use those, it and move it. Boop, boop. Now the next one will be, okay, I need to move the clock line. Wait, why didn't I move this one? This one, edit. Guard ring around it, or in the resistor right next to the sender, so you can tune it to prevent reflections. You mean like let me show you here. You mean like to the ground here, like an extra resistor to ground for tuning? Maybe I will add it then. No serial resistor. What? So no serial resistor. Oh, you mean for reflections? Oh yeah, all right, yeah. So these are, if I want to try open collector, but I will probably not populate them. Maybe only on, no. This won't be fast enough. If I want to it will be a huge power loss. I picked them in series and I want to test it for now if I even need those, but I have planned them in, so they're here. These are the 3 resistors. All right, the clock line here. Let's move that one. Have you tested that, like on the scope? Do you have like documentation, like how that, if this working, or like I would be really interested what your results are on that. I mean, I know you're not having like a bus that is as long. Yeah, that's not huge. I need something like what is? Huh? Move it! Why isn't that connected? You Oh, really? Wow. Okay, so let's do this. One question. Oh no, did you fail CE testing at some point? One question. So, we have signal coming from this direction. Oh. Oh wow. Which Matthias? You fixed it, yeah. Oh wait. Okay, yeah. Since when does he do electric stuff? This is a woodworker. That's why I was confused. Uh, wrong one. Okay. All right. Oh, that's a good comparison. Okay, you need to watch it. Wait. Let me do.
Sound.
Nice
And with high
experiments.
frequencies,
Yeah.
wire
Yes.
behaves very similar.
Is that the wood guy?
And you can actually hear the sound wave traveling through the hose. It actually bounces off the end of the hose and comes back. And that's how you get that sound. And with high frequencies, wire
amazing
behaves very
explanation.
similar, just a million times faster. And I got what's left of a big spool of Ethernet wire here. Now I just need something to send pulses down it. And I'll be using this MH098 1 gigahertz scope that Rigel sent me
make
for
good
review.
video.
And this scope has got
Oh,
a
yeah,
built-in
that's- he
function
got the
generator which
Rigel
the
scope and
and
then
I've just set it to a maximum frequency. And the waveform I got here has got a rise time and a fall time of about 8.5 nanoseconds. But I wanted
that's
something a little bit
100
sharper, so I
megahertz, or
programmed this
what's the-
Raspberry Pi
the
Pico
signal
to
generator?
generate very sharp pulses on 4 output lines simultaneously, so I get a little bit more power coming out of it. I
Clever.
just grounded it to
Et
my
double
scope,
as
so
a
let's have a
review.
look at what comes
Deal.
out to where the result
fair use. We
is.
need to be careful.
And that is.
But I don't think,
much
like,
smaller
Matthias,
than
we are
scope,
sharing the same
way
name,
spread
so-
out. So let's send something more complicated down the line. This pattern. And we can see there's still remains of our individual pulses,
Wait,
but
do
they're
we get translated to
kind of slurred.
German?
So if we count each of these
Huh?
things here as a bit, I'm sending 125 million per
Do we
second.
get translated
But
to German?
that doesn't
What?
get me to a gigabit per second. But on cables like this, there's 4 pairs, and they use all 4. But that only takes me to 500 megabits per
The
second.
text to
But
speech.
gigabit Ethernet actually
Only
uses
4
multiple levels of
GHz
encoding,
sane.
so they use 8 levels. So you actually have 3
Oh yeah, text to speech. Now you can hear it because I turned on my desktop audio. Yeah, Quinn, you're in my ear. That's why I don't need to read my chat. I'm listening to all the chat while I'm working here.
bits for every
will
one of
turn it
those
off in a
pulses
second.
that I've sent at 125 megahertz. And then they use some fancy error correction, which then gets it down to 1 gigabit and makes. And we get another reflection here, and then it bounces back, and another reflection. So we have.
Oh,
signal
so
bouncing
you
back and
can
forth
you
and
can
back
see
and forth and
actually
back and
the cable length.
Remember-
But this is I mean, what was the length of his testing cable? We are working at okay, there will be some ringing maybe, but we are working on like not gigahertz, like 20 megahertz. That's what I try to achieve at least. And the length is only 20 centimeters, more or less, or 16.
Q. Listen for yourself. Click connect on this page. https://bitluni.net.
I turn off desktop audio for you again, so you won't be listening to the TTS. Some people find it annoying. Yeah, you can turn it on for yourself. Oh wait, the length of beads and cable. You know, interesting part. We will measure the length of the SPI and then match it to the frequency that we want to desire. So we get, when we bounce back, it amplifies the, no wait, it won't amplify, it will be overlapping it. That's the worst. Yeah. Ah, 32 devices on one bus. At least 32 clients. So that will be a stretch. That's what we test here. What is the highest speed? Yes. Let's see. Let's see what happens. Yeah, but the project is it's more of a hierarchical English hard hierarchical design. So the actual thing, like the bottlenecks, will happen at the ends of my design. Where is it? Do we have the design here? So we are currently click here to reconnect. We are currently talking about 2 half lines here. This will be one of the buses, but then we need hierarchical. Holy flame. Then we have this bus. It needs a higher bandwidth than this one here. So this will be a stretch already. And then we need even a higher, oh wait, yeah. So this is the first bus. Then we have the second level, which is here, which is longer, needs higher throughput. Hierarchical. And then we need another one that goes through the connector. That will be, and then all the 64 PCBs will be consolidated. Look at that circular here. It's not popular. Look at the density of the PCBs. Like if we look from the bottom, yeah, the budget is 15K. It's 65,536 MCUs plus, yeah, plus this is my nemesis. This will be the end of bitluni's lab. End of my wallet. Yeah, so the sponsorship pays for that. I hope it will work. We want 1 MCU per pixel, and then we will do a Mandelbrot. The most expensive Mandelbrot in the world. A gazillion FPS with a iteration depth of I don't know, 10,000. You can render in HDR 8. Oh yeah, there are LEDs. Of course they are. No, they are RGB. Look at that. Look at that. Quinn. Here we go. Not addressable, of course, because addressable are so power hungry, and we need like to limit the current, so this whole device won't consume more than 16 amps AC. No, not enough. Power delivery. No, 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 no. This will be AC powered. 2.4 or 2 point, yeah, 2.4 kilowatts. Yeah, you need to do the calculation. Not enough. Not enough. Not enough. Let's do a simple calculation. Okay. We have 2.3 kilowatts. Wait. Okay, this is watts. This is watts. Then let's divide it by, okay, we need at least like 2.3 volts or something. So let's say we have, okay, we have, wait a second, 330 times 16 amps, then 330 times 16 amps. Oh, this is the watts that we can do. Let's divide it by divided by 2.5, let's say. That's the voltage that we need. 2.5 for the LEDs and the MCUs. Most of them will need a little bit more. Then divide that by 65. Oh, we should do the correct number. 536. Then we have 22 milliamps for the MCU, including the 3 colors for the LED. So we are at our limit for the European power outlets, which is only peak 16 amps. The American ones are like 10 amps at 100. What is it? 10 amps at 110. That's way less than that. We need like to really scale down everything, and we need 10 milliamps already for the MCUs. So this will be a stretch. Either we require in US we require a 20 amp fan. Yeah, this is considered, we wanted liquid cooled, like submerged cooling. That's why it's in this container. But in the end, I probably will circulate the air like that. It will be basically a 2 kilowatt heater. Submerged cooling with passive cooling or active cooling on top, like with. But yeah, this will be just a heater with, I don't know. Your fan takes 27 watts. Yeah, so that was also a suggestion to run it off lithium batteries, basically. We don't have... No, we are limited LEDs. If you consider... Oh, wait, you're right. If we consider the... Oh, what happens... Okay, how much lumen do we get from LEDs if we run like 1 kilowatt in LEDs? How much lumen is that? 1 kilowatt in LEDs. Oh shit. Wait a second, I never considered it might be too bright. Bright as the sun. That's why I put 1 kilowatt, 1 kilo ohm resistor in front of the LEDs, because I really want to limit the current massively. I don't want like 20 milliamps. Inefficient, 50 lumen. What is then 50,000 lumen? What is with 50,000 lumen? Nah, that's inefficient. It will be like, because it's not white. Yeah, the issue might be that they destroy like from the power, like okay. What did we, 50,000 lumen? Extremely high. High-end flashlight, 10,000. No, it will destroy itself. It will delaminate the opposing PCBs. Look at that. We have like, okay, I mean, we divide it in 64 layers, but if I make them bright, I should make them white. We need white PCBs, otherwise it will basically destroy itself. The heat will be consumed by the PCBs. What do we do? Do we do white PCBs then? We need to reflect. If we are like, oh shoot. The scale of big numbers like this. Look at that. Look at that. Yeah, if it will get brighter like to this side, but we can't let it like heat up from. No. Okay. 3 milliamps. We need to calculate what size of resistor we will take for coloring to water. We will take a different power supply for the LEDs, because like my LED wall has 2000 LEDs. Okay, my LED wall, the fourth one, which is quite bright, had 1800 LEDs. So it's just 25 that many in this confined space. No. But this was at 50 milliamps per pixel, and we have only like 10 or 5. Yeah, no, let's not go that route. That is crazy. That's too much. Okay. What? Okay, let's. This is. Yeah, let's check. I have. The solar says. You know what? If we make it the self-propelling thing, we put it on an axle in the center, and since the LEDs are pointing in this direction and there is black on this side, it will just be like a sail, and this will automatically rotate in this direction. It will start spinning. If we hang it from the roof, like, it will start spinning on its own at this. It can be reach. It will reach like almost speed of light. Shoot, that's stadium lights. It's so crazy. What? No way. I need to. I need to put this in consideration, my friends. This is crazy. This is too bad. Okay, let's put it here. Trick. Laser. It will. No, no lasers. I want to keep my eyesight. Peltier to use what? Peltier, yeah, self-propelling. On the backside, I will glue them on the backside, and then we need like a cool side as well. So I'm not sure how much we can get there. Okay, we need let's see if we have 10 milliamps. We can check the lumens, and I have the data sheet actually here. Chinese brand. Okay, so we have a relative lumens intensity. So let's take an average. We will, if we do 3.3 milliamps, that will be roundabout, I say 1 lumen times 3. No, we can add it. Actually, we can add it. The average on this here, yeah, it's round about 3 lumens. So we have a number then. How do the resistors dissipate heat? They will dissipate some heat. How does it work? So if we limit the current to only like 10 milliamps for the whole thing, relative to what? We have 3 lumens. Oh, so the actual dissipation, so we get not 50,000 lumens, we will get 150,000. So a whole stadium, all 4 corners. No, this can't be true. This is then like cop lights. If you look in the cop light, like the 100-watt ones. Oh, I will take the voltage is 3 point. I think I took the lowest one because they have common anode. I will take 2.3 here. 2.3 is the voltage that I will take. So actually that might be, I don't know. That's for current. I mean, so that doesn't matter. Yeah, 2.3. I will have a separate power supply. So the idea is I will have like the common anode, we will have a power supply that drives them with 2.3. I mean, we can tune it. And then the MCU will only control the ground side, like the cathode. So we will PWM the cathode, and no, not a single color. Yeah, we have, look at that. So this is the voltage for the anode. So here's the incoming voltage, 2.3 volts, and we have 3 connections for RG and B, which are basically, we can either do pull-ups, pull-downs, like if we want like really dim, which is not dim with 65,000 ones, we can use the internal pull-down. Yeah, I need to regulate it with the PWM then. Or I use different resistors in that case. We can calculate the individual resistors, or I use just a single value and do it in software later. Because we limit the current anyways. I don't know what the we need like for feed voltage 2.3. That's what I say. That's the minimum. We can feed it a little bit higher because we can probably control the output, and I will do an individual regulator per PCB that converts like 12 volts to whatever I set up here. So maximum voltage is 3.2 anyways. Yeah, I know, red is... So this will be probably like green and blue are the same. Green is basically blue with some phosphorus or whatever, and red is a different one. So probably we need here, we can change, oh, you know what? Maybe we should calculate the resistor values. Let me put it on my to-do list. Thank you for noticing that. We could also try to calculate, but look at that, red has also a lower lumen output. So we need double the current for red to output a similar, almost double. Okay, green has a different curve because we have some saturation for the phosphorus. Needs more, yeah, needs more. So basically, in the end, it will be the same. I'd maybe just use 3.3 volts and then vary the resistors per color. Yeah, but does it matter? We can also use like 12 volts. The issue is if we have like a burned LED or whatever, we get 12 volts too. Why do we need like to... Okay, If we use only low voltage, we can... What gets hotter with more voltage? Or, oh, you mean like lower voltage because of the resistance? Uh, hmm. Yeah. Yes, the current matters. Voltage times current. I want to keep like the voltage as low as possible to have them driven like at almost a minimum. But we will be able to control that. I want to be able to trim that as well. We can see forward voltage, and that's the current. Doesn't matter. Temperature. Uh-oh. They melt. At some point they melt. Lower than 80 degrees. Beeps. Uh-oh. Ambient temperature. Red degrades here as well. Here. That's 1 by 1 millimeter. These are the similar ones to, not to this one, to the, not, they are like used on these ones, but they're even smaller than this. This is like a bigger package. 1.1, they don't have like a frame or anything, they're just so we don't want to drive them at 50 milliamps. They will melt off. Red ones? Yeah. So we want to run in blue. Yeah, but we are driving it at a higher voltage than it requires. Oh, wait, we can calculate that. Okay. Yes, Cherenkov, that's what we want to do. Okay. Okay, another task to do. This is insane. Imagine if we give it the ability okay, we need some, I need some way or form of controlling it so it won't explode. If we get like 1 kilowatt of LED power out there, this is in this confined space. This is so hot. Yeah. So the question, if it's a display, it's quite dense, but you will be able to see some sort of volume if you look from this side. But I don't think you can see a picture because the LEDs, it will be populated only on one side, so it will be more like a hazy, colorful indication. It will probably just pulsate like that, or rotate, or whatever it will do from the center to the outer. Whatever we can do whatever we like there, and yeah, let's hope we can maybe display utilization or the status, what they are doing right now. I don't know. It will be strange. Maybe we'll start with one PCB at another one, and more and more and more and more and more and more. Oh, you know how a PWM drive, if we want addressable LEDs, the WS2811s, that adds another 10 milliamps or something. They are so inefficient, we can't use that, and they are expensive. So it's like 10 cents. I don't know how much are they. So any added component that's not a passive is so expensive at this scale. Let me check. LCSC. So we have. Alright, we can get them quite cheap for a cent each. So it will be only 65,000 $650 just for the. Yeah, so the only issue that I have right now, I have another MCU planned that doesn't have 3 WMs. So we will probably put the WM on green and blue and leave the red. Small Hadron Collider, yeah. Photon Collider. 1 cent per WS. Right, no more components. We also don't have space. Max, yeah. This one is already hard. I mean, we have like one more timer pin here. Oh, I wasted so much time talking. This one is all right, but the one that I want to use, there the PWMs are on the same pins as the SPI and stuff. So can't use. Probably then, I don't know, if we really want to, like, maybe I will just use this one. The other ones have more RAM, faster integrated flash, are just a newer generation. 2 colors. Yeah, we can use one like software PWM color, or I don't know if there is. I can't. It's not. They're not announced yet. The ones that I. Let me check the data sheet. There was one issue, I believe. So. Oh, the data sheet is long, and I have one only in Chinese. Okay, we have Misomosi, SCK, SCS, then timer, PWM, oh, we have 3. No, that's timer 2 remapped, timer 1 remapped. Maybe we have an option, I'm not sure yet. How didn't I see that? Yeah, the issue on the chip, on the other chip, is that wait, 95D SCK SCS. Yeah, I didn't see that. We have timers. We have PWMs and timers. I can use probably the timer to use it with timer 1, timer 2, and PWM 10. Okay. The other chip will also work. I believe so. Not sure yet. Okay. Eh. Can you divide 65 LEDs into different RGB LEDs to make a small pixel from a distance that colors should merge and you can save package size? Yeah, no. I really want like an indicator per MCU. You know like on my video with that one, let me okay, so we have here, these are 160 CPU. You can see, okay. Okay, so you can see for each of the MCUs on that one, like all the MCUs working. And I thought, oh yeah, I want to see that on the Ultra cluster with 65,000. No, we have enough PWMs, that's all right. We can use the timer thing to drive it, I believe. I need to read it. I have only the Chinese data sheet, but I saw there is like they are quite timers and PWMs are quite similar. Yeah, what I thought is, okay, I need like this. Yeah, no extra components. If you want to display like the current utilization of each of the MCUs, you need 65,000 indicators. On QVGA, that's basically a pixel. If we use 4K, 4K we can use, we can display it on a 4K display, which will be, let's calculate how many pixels to display like these things. Oh, that's the wrong calculator. Where's this calculator? Here we go. Let's calculate. What is the 4K resolution? I have the 65-inch 4K LED, so 3, 8, 4, I'm tired. You can 256, 15 pixel per benchmark. Perfect. We can show it on 4K. Display like the utilization. 15 pixel, one pixel for separation for a frame, and then beep. We can't even on 15 pixel we can't even display the number of the MCU. We can only like maybe digitally, like binary Morse code, display the number which MCU it is. This is pure madness. I hope it works. This will be such a bummer if that... No, 15 pixels. What are you talking about? We have like 256 by 256. So we will have like 4 by... Wait, 5? Did I did the math wrong? No. No, we have 15 by 2160 divided by 256, 8 by 8 pixels, 15 by 8 pixel. Hey, Mr. Koo, what's going on? All right. Yeah, we didn't do much of our layout, but we figured things out, and I want to end stream quite soon. Let me move that around. Okay, we have I didn't consider that we can do the math for the LEDs before I start doing that here, because that's actually not that interesting. Why am I here? At SPI Mesomosi. Yeah, we need to put the clock in the center so it's closer to that move. Here. Now we can route the clock with... I'm wondering if that will work. Might be tight for our... That's what I wanted to test. 5, 6, yeah. Yeah, that's one. That still works. Oh. Oh, barely works. No? What's going on? Let's reroute it. Still works. Nice. Okay. So with the impedance matching, we get that one working as well. These are the LEDs. We don't need that. That's cool. And we have the chip select, which changes from each of the lines that we will ingest here. That's actually really cool. The only thing is this resistor needs to move slightly, so we can move this one somewhere else. Okay, cool. I think we have a fitting layout. The layout on this one will be just mirrored. The issue is probably, I'm not sure if this will work out as well on the other side. I hope it will with the LED. No, it will work. Look at that. Here, it's even closer. It's on the same side. Okay, this will work even better. So I have a plan, Pips. I will try to order that with the standard. No, I don't mirror it. I rotated it by 90 degrees, but the layout is mirrored. So I have the LEDs on the other side of the chip. The two rows. I just want it like symmetrical. That's why it's like that. And I think this will work out. I hope that I can fit all the connections. That's 32 connections here. The vias are not the right size right now. I know it was a joke. Let's calculate on the LEDs, the LED resistors. So we can consume up to what is it? 10 milliamps per wait, let's calculate it correctly. So I think parameters. Heating turned off. Whoop. Absolute maximum rating. Okay, milliamps. Code runs in RAM. So this is without flash. That's the how you will run it. So I will guess it's like 10 milliamps. Oh, you can see. So this is milliamps. 10 milliamps. That's basically at 60 megahertz. So I guess we will run it more or less on that. If I consider maximum for maximum of 10 milliamps for the LEDs, maybe we need like even two power supplies, just one for the LED and one for the MCUs, so it will never, the MCUs will never yeah, we have to go big or go home. mm. It's almost a year. Like it will be just a year after I did this thing. Yeah, and I really don't want to, like, the power supply. I don't want a mess on my power supply for the MCUs. So that's the plan. That's why all the power will be routed on the backside of that. So this LED power. Oh, there's another one missing for the MCU power. Where do we put the MCU power? Oh, shoot. That's a tough call. I might need via somewhere here, because we have the clock line now here. Okay, we could put the clock line over here, so we have space here. I think that will be more smart. Yeah, we can put the clock line here. That's SPI Mosi. All right. That will be like power like that, just filling all the powers. All right. Calculating LEDs. So we are considering now, we want to use 3 milliamps per LED max at 2. Let's assume 3.3 volts, or if we consider 5 volts, because power supplies with we can trim it. Let's do that. Like if we run it at we will have 150,000 lumen if we drive it with 10 milliamps per LED. So if we calculate, yeah, it is. But there actually we have, wait, where is it? Where's my sheet for that? Here. They're scaled for maximum rating 50, 40, 40 milliamps. That's the rating. What? Pulse forward current. Okay, so that's pulse, but continuous, whereas forward current continuous is 10 milliamps. So running them at 3 milliamps max, we consider that like, okay, if we use like a pull down resistor with 50 kilo ohms internally, it will be slightly dim, no matter what but why limit? We can't change that, you know that. Okay, one issue that we have, which might be good for that, we have a limited ground here. So the current needs to go like through these wires, through the MCU, into the ground, which is also like one thing to consider. But yeah, I'm doing PWM. I don't want like to light them at the maximum power of 3 milliamps. So I don't want to light them like on intentionally all the time like that. I just don't want everything to burn out. That's like the upper limit. Depending on bit depth. If I scale 3 milliamps at 5 volts and I run them at half of that, that will be 1.5 milliamps. Yeah, 8-bit. Or timer we can check for... That one supports, I think, if we use this one, PWM. I think the timer peripheral uses PWM. Where is it? Or is it PWM here? Okay. They are, I think, 16-bit, 5-channel, 16-bit, 8-bit, simple. Quindor. Let me think. Let me check that. Provides 5-channel 16-bit or 8-bit PWM. Oh, okay, so that's we can do 16-bit on each of the channels here. PWM 1 to 5, which are on this one here. Wait. PW 1 till 5, 3. Yes, they are 16-bit. Yeah. So that is that. And we can always lower the voltage. So we can go down. I would calculate, because getting a power supply for 5 volts is way easier than doing like individual controls. I don't know, 2.3 volt output. 3.3 is more common, but not high currents. 5 volt high currents is available. Yeah. Okay, let's see in what ballpark we get here. Okay, let's do an LED calculator. Boop. Power supply, let's do that. LED voltage drop. Yeah, I know. 1 point, yeah, okay, let's do, yeah, red, let's do that. Current 3. $1.1K. So it's already undersized for red. What do we have for 2.3? 910. So 1K is actually not that bad. we need more current for red because it's dimmer, and the other ones stay like at 900. It's a little bit exceeding, so maybe we should do 2K or what's one. Total power consumed by the resistors. Oh. That's with 5 volt. 3, yeah. Okay, let's do number of LEDs. Okay, so let's. Oh, damn it! No! What is it doing? Oh, in parallel, no! Total power consumed. Three milliamps. Yeah, getting closer to the 3.3, 1.8. Let's see, 1.8. Yeah, we need to keep it below because we have like resistor. The drop of the voltage drop by the resistor is already. Yeah, no, that's why we get lower to breathe. Yeah, you know what? We will keep the voltage down. I will just get like some proper regulations here so we can drop that, and we also need to put fuses in. So if we are like a current spike that exceeds what our maximum rating that we calculate here, that it will turn off or something. Fuse like that. Johnny, I know which video you linked. But the video was already made. So this is Styropyro video. It was already made by photon induction, the British guy that does those experiments in his backyard or in his attic. He did already like a super big. It is exploding. I didn't watch the Styropyro video because I watched already photon induction video on that topic. All right. So running it at 2.3 volts or something above that is already. I would say let's go for current rating of 2. So we have a little bit. Look at that. That's 270 ohms if we run it at 2.3 volts. If we run it at 3.3 volts, we drop almost as much power on like infrared LED. The 3 infrared LEDs that are creating heat down there. .6 milliwatts. Watts 65 times 6.6, 400 watts. That's not much. Yeah, so if we run it at 2.4, oh, typical voltage. Oh, you're right. Maximum. So let's do put 2.7. 6.7. 2.7. But if they rate it, I mean that's like a minimal forward voltage. Okay, minimal, typical. 3.2. If they don't light up, that's terrible. Yeah, I would do that, a DC-DC converter. Maximum is 3.2. If we are unlucky, because we have like, oh, that's 6.6 if we do 750. That's on 1.8. Wait. That's one of them. Two milliampere. So red should be 750. 3.2. No, worst case scenario would be 2.2. 510. So actually we need smaller resistors. 510, and that's already quite high. Milliampere. 6. All right. Current source. No, we can't do current source because we have different currents on all the LEDs since they are driven individually, not like on average we will have a different current on each of the LEDs. That would be for parallel, like, I don't know, lights, whatever. Yeah, not happening that. All right, I think we need to take, if I take 1 kilo ohm linear driver, yeah. Higher current rating. Let's see. Let's see if there is specs on that. Yeah. All right. So giving it 1 kilo ohm is actually right ballpark, more or less. 510, and what was for in 1.8, 750 and 510 might be more suitable. If I use, considering the lower output of the red one, I might want to put it on 510 then. Damn it, I think I didn't buy the right resistors. Do I have so many resistors? Did I order resistors? Oh shoot. What did I buy? Oh no, I only bought capacitors. Okay. Let me get a reel of resistors. What values? 404. I don't have like a bunch of 404 resistors, so yeah, 520. Do we really? Only the test one. The test run. I will not, unless I buy. Oh no, it's not K. And let's add a node. Not really. I mean, we could do it. Okay. Fix it in post. Ah, 65,000 reworking. So if you consider we get where's my LED calculator? Here. So this is 750 ohm if we want 2 milliamps. And then if we do 2.7, no wait, we need the typical voltages. 2 and 2.7, okay? Okay, so let's do that. 2 volts, 620 on 2.7 is 270. Oh, wait. Yeah, I know. I don't want like to rely on PWM as for maxing it, so I want the max. Okay, this is actually running at this voltage. What was it? 2 at the typical one. So it's like double the current. Double the ohms, but then we need to take a look at here. Okay, typically red luminescence shouldn't be like double of that, but more or less we could, like red and green, this one drops off at 3 milliamps. This is what we will drive it the most. Look at the difference. We need like double the current to get the same output. If more than that, look at that. If we have like, this is 1.5 milliamps, we need almost 5 milliamps to achieve the same light output. So actually driving it hotter is better. Let's test it. 2 volts, we 620. Okay, maybe we 2.7. Let's see how much we get. 270 at 2 milliamps. Now let's go, that's 2 milliamps, and let's go for 4.5, 270. Okay, so we get, instead of 2 milliamps, which is here, we get 4.5, which is here. So we get quite the similar output there. But I don't want to drive it with 4.5 milliamps. But usually you don't do red as bright. Red is only 1% of 10% of the light if you mix it RGB, like RGB. We have like 11%. Yeah, 11%. So green needs to be brighter. Do we consider that? Damn it. I don't know. I think that's enough for today, peeps. I'm quite happy. I will probably weight them for the... Yeah, okay. I mean, with 16-bit PWM, way happier than yesterday. Yes, I'm way happier than today. This stream, woo, that really helped me a lot. We have figured out so many things. The ridiculousness of this project just unveiled its true power, true colors. Okay, if we drive it with, let's calculate, if we drive it, consider driving it at 1 milliamp, that will be, yeah, 0.5, and then this will be driven maybe hotter. That's three times 1.5 lumen times 65,000 is more than stadium light still. If we run it at the rating of maybe we can do X-rays with that one. Who knows? Amazing. Yeah, Quindor, you helped really a lot. Also considering the top layer impedance to match the bottom layer, that or not the bottom layer, the actual signal layer. What's going on here? This is the weirdness of KiCad. Kink. Oh, one thing, Quinn. How one question here. We have the signal, the host is on this side. I don't want right angles. Right angles are bad for signals. But do I do this here, or do I connect it like with a right angle? Like that. What is better? Do you know that? I don't know if a hard one, huh? Right angles are always bad. I mean, already the via is a right angle here, and then we get another right angle. Johnny, what's your suggestion? Trivia, yeah, we are disruptive anyways. I mean, okay, we are traveling along this path here. So current is traveling on the surface. So we are going here, then there, and there will be, yeah, there is no right angle anyways. In that case. Drill B. Holy hell. That's a good one. Yeah, maybe I ask. Okay, that's the last question for today. ChatGPT. Okay, let's ask ChatGPT. It helped me with a lot of questions on fast signal. Fast signal lane should not have right angles on PCB. Does that matter for connecting lanes on different layer through a via? I never get through right. Right angle. Or should I angle the trace more to point towards the emitter of the signal? It's bullshit with that I'm return current behavior, no geometric pointing. Okay, so local impedance, discontinuity, current crowding, reflection risk, manufacturing, etching, artifacts, historical, blah blah blah. Stub indactance, barrel capacitance, reference plane change, if any, return current path disruption. Yeah, that might be a thing. Not a problem. Left angles. The no signals do not propagate like particles being aimed. That's a good explanation. So, waves guided reference plane. Oh yeah, alright, okay. Then this, I would consider this explained, and let's fix that one. Boop! We get shorter, okay, shorter traces here. That's okay, cool. Yeah, whatever, like that. Nice. Look at this one. Teardrops. Oh, foo. Thank you for... How do I configure teardrops? Constraints. No, that's field strategy. Teardrops. How do I turn it on? How do I turn it on? How do you use teardrops? I learn even more this time. Is this like a track or via property? Oh. Add teardrops on via track connections. Ah! But doesn't that change the impedance on this on this here? Foo. What is the expertise on that? Yes, teardrops are generally a good idea for vias, especially the larger ones, but for mechanical manufacturing reasons, not signal integrity. Manufacturing yield. Oh, actually, that's not bad. I want a good yield. Main benefit repair tolerance. Negligible. Okay. But I like the teardrop if it improves the yield, especially if we have like offset here. I would consider that. That's cool. That's cool. That's cool. That's cool. All right, peeps. I will go to bed right now. Thank you very much. I learned a lot today. We fixed a lot. I have some more stuff on my to-do list, but I also found some solutions, and we this. Oh, Mr. Triad, no worries. You're not annoying. I met different people in the past. They were annoying, but you are not amongst them. This is really. Oh wait. I'm just checking. Wait, I have wrong centered here. Yeah. See you next week, where I will show you what I ordered. This will be amazing. A cluster. I will. Yeah. Good night, everyone. This will fit. This will work. I know it. Peeps, I know it. We have, I think, enough space for all the traces. Bye bye. See you next time. Thanks for joining the stream. And thanks for the donations, Fu, and for the sub. We got a sub on... who was that? On Twitch. Iben Miller. Thank you. Did I respond? Yeah, no. We are all fine. All right. Bye bye, everyone.